Take two uncharged conductive plates and put them very close to each other, a micron apart, in a vacuum. What do you think will happen? Leave your answers in the doobly-doo.
So actually, plates move closer together. What?
This is the Casimir effect, predicted by Dutch physicist Hendrik Casimir in 1948.
But if vacuums are just empty space, then there should be nothing there to make a force, right? So how are the plates moving? Wizardry! Close. Think quantum.
Quantum theory is basically physics for very small, like, atomically small things.
Don't worry, I got you.
We normally think of forces as particles interacting with each other, right? So one particle might give another particle momentum, and that causes motion. In quantum field theory, the particles are not actually directly interacting with each other, but rather exchanging virtual particles that carry momentum from one particle to the next. Now, according to the Heisenberg uncertainty principle, you can't know the position and the momentum of a particle at the same time. Same goes for time and energy. So if you know the momentum of the virtual particle, you don't know where it actually is or how long it will stay. Basically, virtual particles pop up and disappear everywhere, all the time.
So why vacuums?
Well, now you know that vacuums aren't just empty space. They're actually full of virtual particles. The wave-particle duality tells us that particles can also act like waves. Think about how waves are distributed over space, whereas particles are localized. If you drop the ball into water, it could bob back up anywhere like a ripple. Its position is spread out like a wave. However, the moment you see it bob back up, you know exactly where it is, and its position is localized like a particle. And just like how particles aren't all the same, waves aren't either. Some waves are thicker than others, so in the small distance between our plates, not all of the virtual particles can fit. However, outside the plates, all sorts of virtual particles, including those with larger wavelengths, are floating around, not constricted by the boundary of the plates. When more virtual particles are bouncing against the outside of the plates than inside, that creates a force that pushes the plates together, aka the Casimir effect.
Finally.
Oh, we aren't done yet.
When you build machines on the nanoscale, like 10 to the negative 9th the size of a meter, parts are close enough that the Casimir effect comes into place, making things stick together. To make nanomachines work, we need to acknowledge the Casimir effect.
This is the future. Now that you know the Casimir effect, we are one step closer.